So I gave WebEx a chance, um, and it so far hasn't worked very well. Supposedly there's recordings because I hit record on all of them, but they're not coming through. So we're going to go back to the old-fashioned method of actually just recording them and posting them on YouTube. So Ahmed, who I was talking to earlier, hopefully this doesn't mess it up. He does recordings for the math department, and so hopefully he'll be able to help us out with recordings. So right now the process is I have to record it on a camera. I'm going to try it on the computer, but usually on a camera I have to download it to a computer, and then I have to put it in Camtasia, then do all the little edits, and then put it up to YouTube. The process takes like 2.5 hours. Right? A lot of it is me not doing anything. It's waiting for it to get encoded and pushed up to YouTube, and waiting for the stuff to get off the media and everything else. But it's a big giant pain, and so hopefully he'll be able to fix that for us. But we'll see. But normally what I've done for these classes is just do that process, put it up on YouTube, and then like the lecture's available like a day and a half later. Normally the homework is due 2 weeks after I assign it. So just if you're remote and you miss the class, right, you lose it like a day and a half. So it's not that big a deal. So hopefully that will work out. But so we'll see. The recordings from the last 2 lectures are up on WebEx. I honestly have no idea how you get access to those recordings. I was told it was very intuitive, and it's not working out very well. It's like most of the remote students that are trying to join can't join. Go ahead.
Well, I was going to suggest like just a repository like GitLab. I'll put all the videos on there.
Yeah.
And just have
whatever, right? But it's going to be not a live process. The whole idea for WebEx is we have 5 remote students. They're PhD students from University of Washington, and the whole idea was for them to be able to like interact with the class, and it's not working out very well. But anyway, everybody enjoy their weekend. Got a long weekend.
So good.
Some people were surprised, like, hey, we don't have class on Tuesday either.
Definitely should.
So, I was actually surprised, but we got a reminder email not to come to work that day. So, last week on Thursday, I guess, we left off on actually starting to encode signals onto the wire. We had talked about a little bit about things that might be on the wire, like noise, right? We talked about sending stuff down at fiber, some of the advantages and disadvantages to that. We talked about sending stuff over the wire, right? But these are all kind of generalities. We haven't actually encoded a bit per se yet. We haven't actually talked about what you actually do for that. So we talked a tiny bit about changing voltages, usually on 2 different wires, so that you could subtract the noise out, right, and do differential. But we really haven't talked much other than that simple kind of voltage change to send that information. So we're going to kind of move on from here and talk a little bit more about that to actually develop a physical layer model. And then we'll, from that physical layer model, we'll start kind of designing a real kind of network. So, in order to encode a bit on a wire, right, what we really want is we want to have something that looks like this, right? 1, 0, 1, 1, that's 2 of them, right, and 0. So if we're changing the voltages, we talk about this, right? There might be a delay in the voltage actually changing, right? So it will come up sloped, and then we'll come down sloped, and we'll come up sloped. And the faster we get that, the more slopey it gets, right? Because we can only change, right? But if we're changing in frequency or something else, right, we actually need to be able to model this, right? So what we would really like is we would like a wave to look a whole lot like this. But of course, we're doing analog signals, not digital signals, right? The voltage is kind of a digital thing, right? Even though there's a little bit of slopes, it's kind of on and off, it's digital. But if we're using waves, we're using analog signal to move this stuff across a media, whether that's in the air or on a wire or in a fiber, right? We need to be able to approximate what this looks like. So it turns out that if you take a waveform and you take its harmonics, which is to take a base waveform, we'll call that 0, and then you double it, you triple it, you quadruple it, and so on and so forth, and you add all these things together because waves add together when you transmit them at the same time, you can actually approximate this. You would get something like, right, and you can actually add waves together to do that. So from an electrical engineering standpoint, you need to actually, this is called Fourier analysis or Fourier series summation, but that really doesn't matter. What really matters is that we can make analog waves that look a whole lot like digital waves. And we can make them so that they are extreme. The more we use this, then we can become an extreme approximation of this, right? Simply by adding different amplitudes at different harmonics of our base frequency, right? And we can become to extreme examples of this, right? We can make it look almost exactly that way, right? There might be little tiny curves at the edges, right? Because it is a wave, but it'll be close enough. Probably closer than our switching of voltages, right? The deal is how much do we need to approximate this wave for that to matter? Because if we're becoming an extreme approximation of it, then we potentially are using a bandwidth that we could use for other things. Right? It might be nice to actually use, if we don't need an extreme approximation and like 16 different harmonic layers to get this, right? Then we might be able to take some of that bandwidth and use it for a different channel, right? So if we're doing on 2.4 gigahertz, which is wireless, right? We might want we might want to have different Wi-Fi channels so that we can distribute them amongst each of them and they can broadcast at the same time. Because remember, when you're using antennas, you can't broadcast and listen at the same time, right? So, but if we're on a different frequency, then that changes things, right? We're no longer totally interfering, right? So it turns out if we just have this 0-1 threshold, right? All we need is something that sort of looks like this. It doesn't need to be fancy, right? We just have to get over the hump. Now, if we had another wave that sort of looked like this, right? While this is a close approximation, it's an approximation. It won't work, right? Because our 1 right here will become basically a question mark, right? And if the wave if our amplitude is too low, right, versus our signal to noise ratio is too low, right? Some of this might be question marks too, because it's not high enough across the threshold, right? But that's the idea of being able to combine waves and be able to send it across a medium in an analog wave and that's all you really need to understand about that, right? Is that we can approximate that. And if we approximate it well enough to be able to discern a 1 and a 0, that's as much as we want to do, right? And we can save that other bandwidth for something else. We might save that other bandwidth to send more signals down in the same channel. We might divide it out into different channels. So we did talk a little bit about clock recovery, I don't know if we really kind of discussed much of it. Who recalls what we talked about on clock recovery? Why do we need like a clock? Well, why do we need clock recovery built into our network versus a highly accurate clock? And why do we need a clock? Do you remember? Right, we're sending signals down. Right, and so this is an analog waveform, right? So it's like we're sending the signal down. If we don't have a clock, we don't know where the transitions are, which might make a giant difference in whether we have ones or zeros, right? You could foresee that if we shift these lines over, particularly like maybe right here, right, it would become very ambiguous whether that's a 1 or a 0. It already is kind of ambiguous. So we need some sort of clock. So we could build a highly accurate clock, right, and put it on both ends, right? So let's put atomic clocks on both ends and send signals and just go. Because they're both atomic clocks and they're at the relative same altitude, right? They're in sync, and so we can send information. We have a highly accurate clock that will last thousands of years, and we can send information. We don't need clock recovery built into our network. The deal is, not many people can have atomic clocks sitting in their house, right? We might be able to engineer a highly accurate clock in some other way, right? But when we talk about highly accurate, we're not talking about seconds. We're talking about microseconds, potentially nanosecond transitions, right? So it really needs to be on time. So what we instead do is most of the time is we build the clock recovery into the network itself. So how would we go about doing that? Any ideas? How do we build it into the network itself? Just throw them out. Any ideas? We could send a signal down the wire at a regular rate, right? So we could have data, and then, but part of that data could be clock, right? We send a clock signal down. So this is kind of the same idea as doing the frame signal, right? We use the physical layer attribute. So remember, if we have a number of different signal steps, right? So it's log base 2 of the number of different signal steps is the number of bits that we can do, right? So this is 4 signal steps, which means we can transmit 2 bits, right? In order to transmit the 3rd bit, we need 8. Right, but what if we only have 7? We'll get into signal to noise ratio on why we may only have 7. Right, that means we have 3 extra things that we can do at the physical layer that can't be bits. Right, so we can send signals down. Right, we can send a level 7 signal, a number 7 symbol, really, down there, and that could be our clock. Of course, that is wasting bandwidth, right? But it could work. Right? Some actual physical, when we get to the data link, some of this is actually used for framing. Right? Because it's a definitive frame without having to encode a bunch of bits. Right? It's a symbol that is lost, which means that those number of bits couldn't be transmitted, but it is absolutely a way to determine the edge of a frame or some other physical layer attribute. So if we had this extra up here, like let's say we could only get 5s, right? We can't use this number 5 to get a bit because that is, in a very simple encoding scheme at least, we can't use number 5 to get a bit because we need 8 levels to get another bit. So we can use this for special things. We can just label this clock. Of course, that uses bandwidth, and we lose the ability to transmit these bits. Is there any other way that we can do it? Could we deduce the clock based on bits going across the wire. Huh? So let's say we're sending a purely entropy stream, right? So random ones and zeros that are fully the entropy is super high on, right? If we're doing that, then the transitions are regular, right? They're not necessarily periodic, right? But we might be able to guess like 6, 7, 8, 9 bits in a row with a normal clock, like a normal computer clock, and then resync based on transitions. Right? Say, hey, I missed this. My computer clock missed this, right, by X number of nanoseconds, right? So I'm just going to adjust my computer clock. And if the transitions are happening rapidly enough and fully enough, like we don't have long strings of zeros and we don't have long strings of ones, right, then if it's happening often enough, we should be able to resync by deducing where that, just kind of taking a look and checking when we're transitioning, right, and adjusting our internal clock as necessary. Does that make sense? Right, it's not that hard of an idea, right? You basically can deduce a rhythm, right? Because the rhythm is happening at somewhat regular intervals, not periodic, but somewhat regular intervals. And so you can deduce when that rhythm is actually supposed to be happening and when the transitions are happening. And you already have a clock that gives you a kind of idea of when it's supposed to happen, right? So you can simply adjust as necessary internally. The problem with that is when we're sending stuff across the wire, what's the most common number in a computer system? Huh? Most common number. If you just went to your hard disk and spewed out numbers, what number would come out most? 0. By a lot. Right? The second most common number is FF, which is a string of ones. Right? So the problem is our data itself, the most common number in our data is 0. Right? And if we're sending stuff and not chunking it up into smaller bits, right? That means that if we're sending a number and it's a 32-bit number, right, that is 32 zeros. And if we're sending, because in your hard disk, right, the 0 is stored as a 32-bit number on your operating system or on your hard disk, right? So if you're sending that across the network and you're not doing any compression or anything yet, right, it's going to be set as 32 zeros in a row because we're doing bits on the network. Well, 32 zeros in a row, probably not good on trying to keep your clock synced, right? Because just like if I quickly wrote a number of zeros on here, right, and quickly asked you how many zeros is that, right? It's actually kind of hard. Right? If you've ever tried to decipher binary or something, or just a long string of zeros for a serial number, right? You actually can draw. You're on paper. You're drawing numbers through them, right? Trying to figure out where the bounds for bounds of 3, so you can count them up, right? The computer has the same problem. It's really good at what it does. It does it fast, but there's no transitions. It's hard to sync the clock, and it's hard to figure out how many zeros were actually there. So what we really need to do is be able to make sure that there's no long strings of zeros. So how do we do that? Any guesses?
Between clocks.
So what do you mean by tick between clocks?
Something just like a flag, just to tell.
So that's what we talked about before, right? We just use like one of our symbols, right, that is above what we can actually represent for bits, right? But the problem is that you lose all the bits in that symbol, right? So if you had 256 different levels in that, and you were actually reading all 16 bits out of it, then you've lost 16 bits just to give yourself a clock, right? So is there some other way that we could do it? We're trying to do it without losing bandwidth. We're trying to do that on the deduce. We want it to look somewhat entropic, right? We want it to be a little bit random so that we can deduce those boundaries. What do we do? Any guesses? We use an encoding scheme. Right? So let's just make a table, right? And it doesn't need to be anything fancy for right now. We can just say that we're going to represent 4 bits as 5 bits. So we're losing a little bit of bandwidth, right? But in a large table scheme, we're not losing several bits, right? We're using just a little bit of bandwidth. In this case, we're using 1/5 of the bandwidth to be able to get rid of zeros. And we could just make a table, right? So we can say that 0, 0, 0, 0, which is super, super common, becomes like 1, 1, 1, 0, 0. Or actually, 4 ones and a 0, right? And then we have 0, 0, 0, 1 becomes 0, 1, 0, 0, 1, 0. Nope. 0, 1, 0, 0, 1, right? And so on and so forth, right? And if we do that, we can guarantee that we're never going to have more than 3 zeros. Right? We can come up with a table that says, hey, these 5 bits represent these 4 bits, and we can guarantee that it doesn't come up. What's the problem now? Anybody see any immediate problems? So if we have, let's give you some more of the table. 1, 1, 1, 0 becomes 1, 1, 1, 0, 1. Oh, 0, sorry. And 1s becomes, so FF becomes 1, 1, 1, 0, 1. Strings of 1s. We have strings of 1s now. We substituted strings of 0s for strings of 1s, right? We can't have 32 in a row, right? Because none of these are all 1s, right? But we can get, I think we can manufacture, just with what's on the board, at least 5, right? We can manufacture at least 5 with what's on the board right now. So what do we do now? We could have another encoding scheme. We'd do 6 bits, right? And as 6 represents 4, and we could get rid of those 1s for sure. But now we're using 1/3 of the bandwidth, right? Is there anything else that we could do? So what about this? What about if I encounter a 1 when transmitting, I invert the signal? So every time I send a 1, I invert the signal. So if it was high before, it becomes low. So instead of, so let's do like, we're going to send 1, 1, 0, 1, 1, right? And before, right, 1 was high voltage and 0 was low voltage, right? So before it was like 1, 1, right? I'm going to do the transitions in the middle because it will become easier for you. 0, and then 1, 1, right? Those are signals before. But if we invert, if we come up with a different scheme, and say every time you invert a 1, remember our encoding scheme already got rid of 0, so we no longer need to worry about that problem, right? So every time we encounter a 1, we invert. So the signal comes in, encounters 1, and then inverts. It encounters 1 and then inverts. It encounters 0, does nothing, right? Encounters 1, inverts. Encounters 1, inverts. Now we have a guaranteed way of no longer having long strings of 1s, at least 5 in our encoding scheme. And we've lost no bandwidth. So this is an actual example of an early protocol. It's called 4B5B, and it's NRZI, not return to zero inverted. But it's a way of encoding, right? And so now we can get clock recovery, because even though we have this non-transition spot here, right, there's, if you look at this, there's no possible place that you can get a non-transition part 3 parts in a row. Because we got rid of all the zeros, and zeros only way you can get a non-transition is having 3 zeros in a row, and this encoding scheme can't, well, I guess this, maybe I wrote it out wrong. This one can have 3, right, but it can't have 4. So now every time we encounter 1, we simply invert the signal, right, which is still readable. And every time we encounter 0, we don't invert the signal. And we can still recover information from that. So the next thing we want to talk about is kind of getting a little bit away from this simple voltage on and off switch. Right? It's not just encoding a wave into a digital form, but actually how we might do that. So what we've been talking about with this voltage is called passband, or baseband. So it's basically turning on and off, right? And where 0 is the nominal value, right? It can be totally off. The problem is in real life, especially in wireless, right? There is no 0 in 2.4 gigahertz, right? The 2.4 gigahertz or 5 gigahertz Wi-Fi bands start at 2.4 and change, and go up to a little bit higher at 2.4 and change, right? So base becomes 2.4 and that low change, right? Let's just call it 2.40. And then you have some other high, right? So you have 2.4 gigahertz, which means that you already have a waveform that's moving up and down 2.4 billion times a second. That's what giga means, right? Billion. So it's moving up and down 2.4 billion times a second. How are we going to encode information in that? And you can't really have baseband, by the way, in wireless. Why? It's hard to have baseband in wireless, right? Because I guess you could have like a baseband in wireless with like our early examples of turning a light switch on and off, right? It's a huge waste of bandwidth because there's all these colors that we could deal with in there, right? We turn that light off, but we can't really use those super low frequencies, right? One, they're not bandwidth efficient, right? What if we're oscillating at 1 hertz? And we're going to go on here at the end of class today and talk about if you're oscillating 1 hertz, you can only send 2 bits per second, right? There's a theoretical limit for that. So we can't really do that, right? Also, our antennas would have to be very, very large. So at 1 hertz, the wavelength for the speed of light is very, very large. Extremely large, right? Around, at 1 hertz, I guess, is around 186,000. We need an antenna that's 186,000 miles wide. Because the speed of light is 186,000 times per second. So if we have 1 transition per second, that's how big our antenna needs to be. Probably not practical. So, we all have antenna. We have an antenna problem. Also, we just have a bandwidth problem. So to jump ahead a tiny bit, right? Over here, if we're just sending a pulse of 1s and 0s, where the top of the band is 1 and the bottom of the band is 0, at 2.4 gigahertz, right? We can send 2.4 billion bits per second. That's a lot. We're going to find out that noise is going to mess with that, because remember, this is the awful band. This is why it was free to begin with, right? But how do we do this? Give me some ideas on. So remember, we have this bandwidth, and we have something a little bit more squishy than this, because we have the whole range for this band. So 2.4 plus a little bit. So how do we go about putting information into that? It's not super difficult. It's really, we've already talked about it a little bit.
So would you just change frequencies?
Sure, we could change frequencies and make it a little bit more squishy, right? So remember, we have, for our theoretical example, we have 2.40, and then let's just say, the numbers probably don't work out this way, but let's just say we have up to 2.41, right? So 2.40 could be 0, and 2.41 could be 1, right? So well, I'm going to over-exaggerate what this looks like, right? But so this is 2.40, and then this is 2.41, and this is 2.40, and 2.41, right? We can change the frequencies in there. Well, of course, there's a lot of bandwidth between 2.40 and 2.41, so we might be able to encode more stuff in there. We get more symbols, right? What else could we do? Amplitude, right? So we could have our 2.4, right? Okay. I was trying to make it look like the top one. I guess it's kind of like that. Anything else? Phase. What is phase? Yes, we invert the signal where the waves become troughs and the troughs become crests, right? Or crests become troughs and troughs become crests. This is actually kind of hard to draw, right? So we kind of go down, right, and then we're up here, right, and then we switch phases, right, which would be like this. We switch the phase. So every time we switch the phase, we could say that was a bit, right? Remember in our not return to zero inverted scheme, right, it was transitions that we were really counting, right? So we can actually just count transitions in the waveform. So those are the three ways to put stuff on a carrier signal, right? And almost all the things that we're going to do that are especially wireless have to do with putting stuff on that carrier signal. So the question becomes, how much information can we put in here? It depends on the coding technique, right? So a guy named Nyquist, in like almost like 95 years ago, I think now, a guy named Nyquist came up with the idea that the maximum number of symbols you could send, symbols, not bits, right? The maximum number of symbols that you could send, right, is twice the bandwidth, right? Because in our 2.4 gigahertz, right, this is 1, this is 0, 1, 0. But let's, instead of doing bits, because that's not exactly accurate, what we want to do is symbol sub 1 and symbol sub 2. That's the maximum number that we can send. The deal becomes is like, what the hell is a symbol? What does that mean? Well, we've already talked about symbols, right? We talked about, hey, if you need, if you have enough bandwidth and you can stick one transition in there as your symbol, you can get 1 bit. If you can do 4 levels, right, you can get 2 bits. If you can do 16 levels, you can get 3 bits, or 8 bits, and then 16 is 4, right? So that becomes symbols. So Nyquist only said symbols, but the next question is, well, how many symbols can we stick in one? Right. So we have two limits. One, this is the number of symbols that we can stick in any given waveform. Right, it is twice the bandwidth, and bandwidth here being an electrical engineering bandwidth, not a computer science bandwidth. Right, and then now we need to decide how many symbols can we stick in a waveform. And we'll get up to the actual equations, but it's not intuitive. It's very intuitive, right? So if I have at any given bandwidth, let's just use our 2.4 gigahertz, right? If I have a noise ratio, and let's just use amplitude to start with. And this noise, so it's very random, unpredictable, right? And this is our noise ratio. And the FCC says that we can broadcast at 30 dB, and we'll get into even what that is, right? And let's just say 30 dB is right here. Intuitively, how many symbols could we, like just looking at this, how many symbols can we send in here? We can send about one. And the reason is this noise can shift any direction, right? But it's measured in a delta, right? So in order to deduce more than one symbol, we need to have twice the width of the noise, at least twice the width of the noise. If we need 3 symbols, then we got to have more than 3 times the width of the noise, right, for amplitude. It works the same for frequency. So in order to be, you need to be able to raise the signal outside of the noise to be able to do it. So in your book, it kind of explains it like this. It starts out with the number of symbols that you have. Let's say you have 4 symbols, so you can send 4 symbols. You can send 2 bits and 4 symbols, right? That means that the noise ratio that's inside of here has to be smaller than the width of these symbol boundaries. It has to be, right? Because if it was bigger, like if it was the size of my eraser's bad. If it's the size of my pen, right, and the noise is right here, you can't distinguish anything that was sit in that area. Of course, the noise isn't static. It moves up and down all over the place, right? And so it's the width of the average width of the noise that we're really worried about. And so if it's smaller than that, that's actually pretty good, right? If it's smaller than that, then if we receive a signal right here, we know that it can be up to the signal boundary below it and up to the signal boundary above it. And we can be able to discern where it is, what line it's closest to. Right? In this case, it's closest to this line. And we say, hey, that was symbol number 3. Right? Which would be in our simple encoding scheme would be 1, 0. Or 1, 0. So it's not super difficult, right? It's actually fairly intuitive. You can get down to the actual limits. This was a guy named Shannon, by the way, who was like a computer science superstar in like the 40s. He figured out all this stuff, right? He figured out that there was a limit on the number, and it had everything to do with the signal to noise ratio, right? So that signal to noise ratio right, was the width of the noise versus the width of your bandwidth, right, your signal. Of course, we're going to talk about, we already talked a little bit about attenuation, right? In wireless, things get quieter as they move along, right? So your signal to noise ratio is changing as you move along. So, but he said that your data rate, this is not symbols like Nyquist, this is your actual number of bits that you can send, is equal to 2 times the bandwidth, and then log 2. Oh, no, that's Nyquist, sorry. That's Nyquist. Log 2. So this is, I'm going to put symbols. They put rate in there, but it's actual symbols. Log 2 the bits per second. For Shannon, your data rate becomes equal to your bandwidth times the log base 10, I believe. Or no, it's log 2 of 1 plus the signal to noise ratio bits per second. Now the signal to noise ratio in this formula is the actual signal to noise ratio. Signal to noise ratio often comes to you in decibels. Decibels is a logarithmic scale. Because we talked earlier about wireless. Wireless was, it is not uncommon for it to broadcast 1,000,000 times more loud than it actually receives. That is not an uncommon, it's not in any shape or form uncommon in wireless, right? But you don't normally want to be able to deal with giant numbers like 1,000,000 because you're out there trying to figure out how many zeros are in that, right? So it's measured in decibels, right? So the decibels is the log 10. So it's 10 times log 10 of the number. So 1,000,000 would become, log 10 of 1,000,000 is 6 because there's 6 zeros in it, right? And it's 10 times that, so it's 60 dB. That's the signal to noise ratio. So signal, they're both measures of bandwidth, right? Where signal is your actual bandwidth and noise is your delta of your bandwidth for noise, for average noise. The problem is that this is average noise. So if we're dealing with average noise, then that means that there might be things that are outside of average, right? Outside of the nominal expected noise. Right? So if there is something outside of the average, what's going to happen? We're going to get an error, right? We're going to receive a 1 when we should have received a 0, or receive a 0 when we should have received a 1. So because these are physical systems and imperfect, right, we have to later on account for this. And we'll deal with that in the data link. So, we already talked about wireless having crazy dB ranges, right? Does a wire have crazy dB ranges? It can. It could, right? And really, it comes down to whether you're designing this system from scratch or you're using an existing infrastructure. So if you're designing this system from scratch, what you usually do is you say, this wire can only be 3 or 100 meters long. And at 100 meters, given the manufacturing constraints of this wire, there is X number of dBs of attenuation at the end of the wire, right? And we expect to be able to pull this amount of noise out because we're using 2 wires for differential, right? So that's like LAN. LAN comes out with a standard that says, at least newer versions, older versions had this too, but they had standards that says your wires can only be this long. You can't have a wire in in LAN that is more than 100 meters long. It's in the standard. And the standard is there because they know at 100 meters what the noise ratio is going to be. And then they build the protocol on that signal to noise ratio. They assume the worst case scenario, right, and they just build it. It's nice that it's copper because there's not a lot of attenuation anyway in copper. Not at those kind of short distances anyway. Right? So there's not a lot of attenuation, and because there's not a lot of attenuation, right, you just build for the worst case scenario, right, and then you build your entire protocol on top of that physical wire. You could come into a situation where you have an existing wire infrastructure that you want to use. Give me some examples of that. Telephone lines. Telephone lines. What service would we use telephone lines to send information over? Huh? We could use dial-up, right? Good old baud modems. Right? So this interesting is that all voice there's actually another guy that came out that said that all voice communication could be represented in 4 kilohertz of bandwidth. The human can't discern anything beyond 4 kilohertz, so there's no reason of using any more bandwidth than that. So regular analog telephone lines are baseband, and they use 0 to 4 kilohertz to encode all the voice communications. Right? So on regular old dial-up modem, right, you simply put sounds through the wire in that 0 to 4 kilohertz range in analog signals, and then you translated them on the other side. And then somebody came along and said, well, these wires are actually they don't have 4 kilohertz of bandwidth. These wires are actually capable of 2 megahertz of bandwidth. So why don't we put information beyond that 4 kilohertz? And we make it passband. And we just encode it way up there where nobody can hear it anyway. It's not going to avoid, and what do we call that? That's DSL. Right? And so now we have a wired infrastructure that's somewhat like wireless, right? It's because we're using an existing infrastructure. And so when you go to get DSL, you put in your address. And it tells you how much bandwidth you're going to get. It's not because they don't like you. It's because the distance you are away from the telephone exchange. Because the further you are from the telephone exchange, the more attenuated the signal gets. The more attenuated, remember, attenuation is just a weakening of the signal, right? So we're going to put in this Nyquist looking, right? And then it's going at the same rate, right? But it's getting smaller. The amplitude is getting smaller. And eventually down here somewhere, it's going to be really, really, really small. The problem is that there's noise on this line, right? If there's noise on this line the size of this eraser, right, we can discern all of this down to here, right? But if we get down to the end, we can no longer discern anything. So it matters on how many symbols that you can stick on this line depending on the attenuation, right? So for up here, we got about 3 erasers full, right? So we can send 3 symbols, or 3 levels for our symbol. Don't get a whole lot out of that, right? We really needed 4, but you can see that sometimes, right, in this one right here, where you get 1, 2, 3, 4, right? So we can send 2 bits on this one up here. Right, down lower, we might only be able to send 1. In a real DSL environment, you might be able to send 256 bits. Or you might be able to send 256 symbols, which translates to 16 bits. Right, so your service would be 16 times faster than somebody that's only getting 1 symbol. Right, or really 2, it's on and off, getting 2 symbols. And then we might also want to actually look how we're going to allocate this bandwidth. So remember, we have 2 megahertz on this copper wire. Right? 0 to what was voice? 4 kilohertz. Then we might want to put some kind of link signal there to discern information, right? But then we have all of this information here that we can encode. Of course, we have interference because these things weren't really designed, right, for digital communication. So while we have all this, there may be places inside of here that we can't use because of interference. Just this has a really bad frequency band, right? And so we'll divide all this stuff up into usable bands, right? Take these places out that we can't really use, right? And then in like modern DSL, most DSLs that you get at your house today, right? They'll take a bandwidth, right? And this will be for upload. And then download. The download is usually much bigger than the upload. Notice that we have an upload and download on the same wire. This is unlike LAN, which is bidirectional. Modern LAN is bidirectional, right? So they actually use different wires to go. So there's no, modern LAN is synchronous because it uses different wires. Right? So we can kind of get an idea now on actually how to design, at least at the physical layer, how we're going to partition up and how we're going to encode information into an actual real network. Now, the encoding that's actually used in DSL, I believe it's OFDX. It doesn't matter, right? Somebody came up with an encoding scheme that they can put information on the wire and get close to Shannon for this whatever given signal noise ratio. Right? So this is a wired network, right, that they kind of predetermine at the beginning what your bandwidth is going to be, right? Because they can figure out what your attenuation is based on the distance because this copper wire is fairly fixed, right? It still has some properties of a regular engineered wired network like LAN, which is that we can predict what things are going to be, right? But what if we didn't have that? What if we didn't have a prediction scheme, right? What if we're going over wireless? And wireless can exist wherever, right? Your speaker can be sitting right next to your leaky microwave. Which, by the way, I used to have a leaky microwave that would kill all the Wi-Fi in the house when you turned it on. This is if you turn on your microwave and your Wi-Fi goes down, you need to replace your microwave immediately. Bad. That is not a good thing. All right. But so we have an environment that we have no idea what it's going to be like. So in wireless, in DSL, we can say, hey, you're X number of miles from the exchange. We're going to give you this data rate because we know what the attenuation is going to be. In wireless, you need to do all that dynamically. So this is why wireless becomes super complicated, right? Because if you have two computers sitting right next to each other, the signal to noise ratio is very low, right? There's not a lot of noise. The N in that signal to noise ratio is very small compared to the signal, right? But if we're communicating across the classroom or we're communicating across campus, right, the signal to noise ratio becomes very detrimental, right? And so we need to be able to deal with this, but we can't engineer for the lowest common denominator in wireless, like we definitely do in LAN. We sort of did it here because we kind of predetermined what our lowest common denominator would be based on distance. In wireless, it all needs to be dynamic. And we need to come up with a way to be able to adjust the encoding scheme on the fly, right, so that we can utilize the bandwidth that we have in the environment that we have. Also, in wireless. Remember, we also have the problem that you can't talk and listen at the same time. So in wired networks, it turns out you can talk and listen at the same time, right? Because it's directional, and the signal you get at the end of the wire is not all that much attenuated from the one that you put on the wire, even if it's a single wire. So you can listen and hear at the, or you can listen and talk at the same time. But you can't do that on wireless. So let's talk a little bit. So I'm going to try to cut down on the amount of physical layer number crunching that you have to do. But I want to talk a little bit about some of that number crunching because it gives you an idea of the amount of information that you might be able to send in any given meeting. So, bandwidth. So we have our 2.4 gigahertz, right? That is 2.4 billion oscillations per second, right? Because a hertz is one oscillation per second. So what does that mean in terms of well, first of all, what does that mean in terms of spectrum? What's the relationship between frequency and wavelength? They're the inverse of each other, right? Over what? Or under what? The speed of light. Right? So when we say something is oscillating, remember my example of my 186,000 mile antenna. Not that you can't have an antenna half that size and be able to discern frequency possibly. But so what it is the speed of light is 186,280 miles per second, or in this class we're just going to use 3 times 10 to the 8th meters per second. It's not exactly 3. Let's just use that. It makes the numbers easy. Right, so it's 3 times 10 to the 8th meters per second. So if we have 2.4 gigahertz, and frequency and gigahertz are inverse from each other over the speed of light, what is the wavelength of 2.4 gigahertz? I'm not asking you to do the math, just tell me the math problem. I'm not asking you to do divide. Or actually, it would be easier. Let's say we have the government decided to be nice to us and give us a 3 gigahertz. Listen, the equation's much easier, or the math's much easier. So if we have a 3 gigahertz frequency, what is the wavelength? Huh? .1. And what's the unit? 0.1 meters, right? 10 centimeters. So, let's do some interesting properties here. Let's say that we have 1 micron. What's a micron? Is what? 10 to what? 10 to the negative 6, right? So micron is, so this is 10 to the negative 1 meter, right? And a micron is 10 to the negative 6 meter. Let's say we have 1 micron of bandwidth at our 3 gigahertz. But we already determined this was 3 gigahertz, right? So we have 1 micron of bandwidth at 3 gigahertz. What is our bandwidth in hertz? So a more important question is, rather than just simply doing the math problem, if we have 1 micron of bandwidth at 3 gigahertz, is that the same bandwidth as 1 micron of bandwidth? Same bandwidth, right? at 1 gigahertz? Think about that for a minute. At 3 gigahertz, we have 1 micron of bandwidth, right? Visualize it. Let's say 3 gigahertz looks like this, right? And let's say 1 micron is our pen width, right? And 1 gigahertz looks like this. It is half, or it's 1/3 of that, right? That's about a pen width. Is it the same bandwidth? What does Nyquist say? In our visualized example, this has 1, 2, 3, 4 symbols, right? And this has, I guess we started there, 1, 2, 3, 4, 5, 6, 7 symbols. And you get the wave right? This has 3 times more symbols than this one does. They are not the same bandwidth. So this goes back to the 1 hertz example, right? At 1 hertz, right? Let's say we have at 1 hertz our wavelength is actually C, right? And so if we had 1 micron at C, right, we wouldn't even be able to fit 1 symbol in, right? However, if we had 1 micron at like a gamma ray or something that's super high energy, right, you might be able to fit gigabytes of information in that micron, potentially terabytes of information, provided you don't irradiate yourself, right? And you usually have to, creating gamma rays kind of sucks on the whole, being able to encode information, and it might be rough too, right? But there's a difference on where that bandwidth starts. And for an extra credit point, which I'm thinking I'm going to put on the midterm, if I said 3 gigahertz, like we did before, which we already determined was 0.1 meter in size. If I say you have 1 micron of bandwidth, notice that if we had a scale where it's getting tighter and tighter and tighter and tighter, right? So this is our light scale, right? Just like you see in visual light scales, right? It's getting tighter and tighter and tighter. If 3 gigahertz is right here, if you measure that 1 micron this way, that is less bandwidth than measuring 1 micron this way, which is also a different value than measuring 1 micron by splitting the difference. It has to be. There's more information on this side. This is why we're going to have this as extra credit points and quit doing it as homework. Because you really need specifics, right? So if they say, hey, what is the bandwidth at 2.4 gigahertz? And if you have 1 micron of bandwidth, you're going to be like, it depends, right? Is that to the left of the scale or to the right of the scale? Or is it splitting the difference? They're all different answers. None of them are necessarily incorrect unless all the specifics are given. So 3 gigahertz was at 1 meter, right? That's microwave. So imagine what you can now send down let's do single mode fiber, because it's used for long haul bandwidths, right? Single mode fiber is a blue laser. So in the color, let's say that your blue laser that you're sending down here, you can encode all the information in that blue scale, right? How much just give me a rough order of magnitude on how much bandwidth is in that. How would you go about finding it? No numbers, just finding it. First, you need to know the wavelength of blue light, right? Anybody got a rough idea what that is? I think it's like 440 nanometers, right? So it's 440 nanometer. Nanometer is what? It's -9, right? So remember 3 gigahertz, which is pretty close to where Wi-Fi is. Let's just call this Wi-Fi for the moment, right? Is at 10 to the -1, right? Blue light is somewhere on the order of about 0.4 times 10 to the -7. It's 440 nanometers, right? So it's about 10 to the -7. That is a long ways down this squishy scale, right? Where the waves are getting tighter and tighter and tighter, right? A really long ways down the scale, right? On 6 orders of magnitude down that scale. And that should give you an idea how much information you could pump through a glass pipe with a blue laser. So what's Wi-Fi? What's modern Wi-Fi on bits per second? Theoretical, which is on the box, and you never actually get that. I think it's 108 now. I'm pretty sure it's 108 because they use 5 and 2.4 together. But whatever, it's 108 megabits per second, right? And blue light can theoretically pump 108 megabits per second with 6 more zeros after it, right? Because it's 6 orders of magnitude more. There's some other things that we will run into when we try to start stuffing information down there, right? But that's the bandwidth that's available, right? Which was why Wi-Fi is very highly optimized in encoding, right? And so this is why we're starting to see really, really large, fat network pipes. The deal is really you're no longer limited by the amount of bandwidth that's in the pipe. You're limited by the amount of information you can squish through a network card to get it on there. That's the limit. Because computers simply aren't that fast. All right. Any questions for today? All right. Have a good one.
Is that the second chapter?
Yes.